Today's lecture is about the force on a current carrying wire. In the last lecture, we derived this equation which gives you the force on a charge Q moving with a velocity v in a magnetic field B, making an angle theta with the velocity of that charge. Now this equation gives us the magnetic force acting on a single charge Q. But when we talk about current, then of course the current is made up of a large number of moving charges, and if each charge experiences this magnetic force, then this will cause a magnetic force on that current carrying wire, and it will be pushed one way or the other depending on the direction of the magnetic force acting on that conductor. Thus, when a conductor or a current carrying wire is placed in a magnetic field, it will experience a magnetic force. And to derive the value of that magnetic force acting on this current carrying wire, we will refer to this basic equation. If L is the length of this conductor, if capital L is the length of this conductor or current carrying wire, then the force experienced by this conductor will be derived as follows. If this charge Q or any charge Q which is making up this current traverses the length L of this conductor in time t, then the velocity v of the charge will be given by L divided by t. L is this distance covered by the charge, and t is the time in which this much distance is covered by the charge. So the velocity of the charge will be given by L divided by t. So if we combine this ratio, that is Q over T, it will give us the current I flowing in this current carrying wire. So this equation will assume this shape, that is the magnetic force acting on a current carrying wire carrying current I having length L and placed in a magnetic field B at an angle theta will be equal to ILB into sine of theta. Now here you can see that this vector L is making an angle of 90 degree. These are the poles of a magnet. This is the north pole of the magnet, this is the south pole of the magnet, and you know that the magnetic field is directed from the north pole towards the south pole. So B is directed this way, and the vector L will be directed this way. This L is actually the displacement vector in which the charge Q is displaced along the conductor or along the wire. So since it is a vector, its magnitude will be equal to the length L of this conductor, and since the charge is being displaced in the direction of the current, so the direction of this vector will be the direction of the current in the wire. So L, the vector L in this case, is directed along the direction of current. Its direction is this, the direction of B is this, and you are observing, or you can easily see that the current and the direction of B, it is making an angle of 90 degree over here. The angle between B and L is 90. So for that particular case, sine of 90 is 1, So the force on this current carrying wire will be equal to ILB. For any other angle phi between L and B, the value of the magnetic force acting on the current carrying wire or current carrying conductor will be given by ILB into sine of that angle. But remember that if this phi is 0, that is if this B is directed parallel, if it is directed parallel to the wire, the current carrying wire, then this phi will be equal to 0, that is the angle here will be equal to 0. And when the angle between L and B is 0, then sine of 0 gives you, sine of 0 will give you 0 result. So there will be no force acting on a current carrying wire which is carrying the current I in the direction of the magnetic field B. But it will be maximum, the force will be maximum if this angle is 90 degree. That is, if this B is directed like this, it is perpendicular to the current carrying wire, then this force will be maximum. If it is placed parallel, the wire is placed parallel to the magnetic field, the force will be 0, and at any other angle lying between 90 degree and 0 degree, the force will have an intermediate value between 0 for parallel case and maximum for perpendicular case.